Hello. In a previous video lesson, we discussed how to use the comparison test as a way of determining if a certain series converges or not to infinity. Now, what we were able to do was be able to take something like this, which is very similar to 1 over 2 to the n, and make a comparison. The reason we were able to use the comparison test was we know that this particular expression is always going to be less than its comparative partner, 1 over 2 to the n. The reason being that this is always going to be a larger denominator than this one, and as such, this will produce a smaller quotient than that one. However, we run into a little bit of a problem if I make a subtle change to the sequence or series that I'm trying to sum. Instead of plus 1, if I subtracted 1, that actually creates a problem as far as proof using the comparison test is concerned. What I mean is 1 over 2 to the n is actually going to be exactly in between these two values. And so the idea is, here I can use the comparison test because the expression I'm evaluating is always less than the expression I'm comparing it with. However, here we can't use the comparison test because we are always going to be larger than our comparison simplified expression. That's why the limit comparison test was invented. It's actually able to deal with this problem, this conundrum, that the comparison test falls apart, then we have the limit comparison test as a fallback. The way the limit comparison test works is really quite simple. It says that, here, let me pause this for a second. The limit comparison test says that if we have two infinite series and we put the sequences into a ratio and then allow the n or the k to approach infinity, if we get a positive limit, then we can make a conclusion. If one of the two series converges, then so too does the other. Or, if one of the series diverges, then so too does the other. So basically, by putting two sequences into a ratio, we're able to determine if there's going to be a finite limit, or, the understanding of where this comes from and the proof of how it works is a little more complicated than we have time for these days. So we're just going to sort of use a faith argument for now, and then later when you get to college, you can play around with the why and the proof and all that other stuff. So here's the actual practice of the limit comparison test. All we have to do is identify the expression we're supposed to be evaluating as a series, and a simpler expression that is very, very much like, but one that we know about its convergence. So I know, for example, we proved earlier in a comparison test that this, in fact, converges 1 over 2 to the n. That's a geometric series, after all. And so we can say these two will be compared into a ratio. So I'm going to compare the two in a ratio, and I get this, which after some mathematical cosmetics becomes that, 2 to the n over 2 to the n minus 1. Now to take the limit, I need to do a little bit more cosmetics, and I'm just going to divide top and bottom by 2 to the n power. That produces this. When we distribute dividing 2 to the n on the bottom, we're going to get 1 over 2 to the n, and then all the rest divide out to 1s. Now if we let n approach infinity, this term becomes 0, and the limit itself is actually 1. Since the limit exists, and it's positive, and since we know that geometric series converges, I can also claim by the limit comparison test that my expression 1 over 2 to the n minus 1, when we allow n to approach infinity, that sum is also going to converge onto a fixed number. So again, the limit comparison test is a little bit more involved because it involves obviously taking a limit of a specific ratio, but nonetheless the idea of comparison is virtually the same. We just find a simpler series whose convergence we know already and use that to compare into a ratio. And then we take the limit of that ratio, and if it exists, we're good to go. Another example right here. See, once again, I like 1 over 3 to the n, and if this was 1 over 3 to the n plus n, I would use the comparison test. Compare this, 3 to the n plus n, over 1 over 3 to the n proper. Because I know that if I add n, this will always be a larger denominator and always be smaller than 1 over 3 to the n. Since this is subtraction, though, that makes this a perfect candidate for the limit comparison test. So I take the geometric series that I know converges, call that B sub n, and then I take my series, I put the sequences of those series into a ratio, and I take the limit. At this stage, I took the limit of 1 minus something. I'll put that in parentheses just to make me feel better. And then the limit as n approaches infinity of 1 is just 1, and the limit as n approaches infinity of this ratio is here. Now that I'm going to have to lope it. In other words, as n approaches infinity, we get infinity over infinity, and so in order to determine the limit, we'll try taking the derivative of both top and bottom. Don't forget the derivative of a non-e-based exponential is the same thing times a scale factor to account for the stretching. So after L'Hopital's rule, it tells me that if I allow n to approach infinity, now we're going to get infinity in the denominator, which means that the whole quotient approaches 0. Once again, we have a limit. It exists, and it is positive, and therefore the series that I was looking at does in fact converge by the limit comparison test. Here's a sample of some of the exercises from your text, and the challenge oftentimes is not taking the limit or using the test, it's finding something to compare it to. So I just wanted to sort of give us some eyeballs, some visualization. So here, this is 4 over x or k cubed minus 2, and if the minus 2 weren't there, if it was plus 2, I would use the comparison test, but because it's minus 2, I'm going to use the limit comparison test. I will produce a ratio comparing these two, because I know that 4 over k cubed is a convergent p-series. We explored that one earlier, and I'll explore it in more detail when we get to a later video. But since this test involves a ratio, we only need a positive number for our limit. So you could just use 1 over k to the third instead of 4 over k to the third, and you'll still be able to arrive at the same conclusion. Remember, I'm not actually finding the sum here. I'm just trying to find out if there is a sum to find. And if I pass a convergence test, then I know that there is a sum, but I still haven't solved the problem of what is that sum. So anyway, the limit comparison test is just comparing a ratio of variable expressions. So if this constant was 4, or if this constant was 40 or 400 or just 1, the limit comparison test will still give us the same conclusion. It'll just give us a different limit. So here, 1 over 5 to the k minus 4, we're going to compare with 1 over 5 to the k. Pretty straightforward. 1 over 2k plus a whole bunch of stuff, we can compare with either of these, 1 over 2k or just 1 over k, because once again, because it's just a ratio of this expression over that expression or vice versa, it doesn't matter how I scale it. What matters, again, is how the variables relate to one another in a ratio. This one, by the way, I was curious as to why they put that in the alternating series section, because if all of these are positive, and I know the square root of k is always going to be positive, and 3, of course, is being added, I can use the comparison test instead of the limit comparison test. However, this is an exercise in practicing that particular tool, so I would put these in a ratio and then take the limit and see what happens. In part D, we have the plus 5 and the minus 2. Again, if this were plus 2, I would use the comparison test compared to 1 over n squared. I can't use the comparison test because of the subtraction, so I'm going to use the limit comparison test instead with 1 over n squared. Finally, though, I wanted to talk to you about letter E. Letter E can be a little challenging, first of all, to figure out what to compare, and second of all, actually applying the test properly. What I usually do is I consider the highest power the most significant as n approaches infinity. So I subjugate 3n as virtually useless in terms of the overall values. So too the square root of 3. That doesn't even need to be there when n gets extremely large. That 3 is going to be so insignificant as to might as well not even be there. So I take the highest power in the numerator and the highest power in the denominator, and I put them together in a ratio. Notice that this is not n to the 5th, rather the square root of n to the 5th, and that's where I got n to the 5 halves power. And then subtracting the exponents, keeping everything in the denominator, I get 1 over the square root of n. That will be the function that I am going to compare with. But that as a p-series, again, this is something we should know by now, but if we don't, we have to understand power series or p-series. If this power is anything except numbers that are greater than 1. That is to say, if this number as an exponent is less than 1, then this particular series will diverge. So I know that this is a divergent series right off the bat. So the question is, can I prove that makes this divergent as well? So to begin with, I set up a limit of the ratio. This is 1 over the square root of n divided by my other series. Notice I took the reciprocal to divide and multiplied. I'm going to multiply top and bottom by the square root of n. What I'm doing now is just some cosmetics, again, just so I can express this in terms that I can work with. So now to take the limit of this particular expression, if I let n approach infinity, still not conclusive. So I'm going to divide top and bottom by n cubed. In this case, I divide by the square root of n to the 6th, which is n cubed, but then the square roots and the square roots I can divide inside. And that creates this particular ratio. Now I can allow n to approach infinity. This will zero out, becoming the square root of 1, and this will become 0 out, and then the denominator becomes 4. So 1/4 is the limit. Doesn't matter that the limit is 1/4. What matters is that the limit is positive and that it exists. Because I've shown or demonstrated that fact, and I know that the series I compared it to, I know that that sequence produces a divergent series, then my series here that's given, where is it? There we go, is also going to be divergent. So that's the limit comparison test. Thanks for watching.